SwayamPrabha. Digital India. Educated India.
Hello and welcome back to the discussion sessions of the production technology theory and practice course. Now, let me remind you that in the last sessions we have gone through the discussion on the two models basically. Those models clarifying the mechanics of metal cutting. Both models are of the thin zone model, meaning that the assumption is that the deformation takes place in a thin zone. I would like to remind you one thing, that this thin zone is not the real issue actually, because real case, because the deformation occurs in a zone. Okay. Now, as the temperature, as the velocity, cutting velocity increases, this zone becomes of course thinner. Okay. I mean zone where the plastic deformation occurs. So, if we are saying that the zone is assumed to be a plane, so that means either we are talking about at much higher speed, even then the probably the zone cannot be very thin. So, it is just an assumption. So, the first model we discussed the Merchants and Ernst model, where the assumption was, there are 8 assumptions, that these are the machining process is orthogonal machining overall. Okay. So, this is a 2-dimensional case, and the principle that has been adopted in that model of Merchants and Ernst is the minimum power consumption during the machining process. Okay. So, for that what we have done is that final equation of the power we have derived through the FC and VC, and that was in terms of numerator and denominator ratio. And then we said that for the power to be maximum, the denominator has to be minimum, and the power to be minimum, the denominator has to be maximum, and therefore, the first derivative of the denominator has to be 0. So, we have taken the first derivative of the denominator, made it equal to 0, and that is the first equation of Merchants and Ernst. That is what it is known as, and that came from the Merchant circle diagram, where it is again based on the fact that the material is rigid, perfectly plastic, and it is moving at a constant velocity over the rake face of the tool. Therefore, the resultant of the forces acting on the chip from the tool side and from the workpiece side, they are the equal, opposite and collinear. Second model that we have discussed is the Lee and Schaeffer model, that is also a thin zone model. However, here the principle is different. Principle is based on the slip line field theory. Here what they are saying is that there should be a stress field within the chip, so that the forces are transmitted from the shear plane to the tool side. Okay. And in that stress field, the entire material is plastically deformed up to the yield stress, and then the slip line field theory has been adopted to say that there is a free surface. So, beyond the free surface there is no forces acting, and the maximum where the maximum deformation occurs, plastic deformation occurs, that is the shear plane, that makes an angle of 45 degree with the free surface. Then within the triangular zone, that is within the chip, which is the stress free, in the sense that is already maximally stressed, there we have taken perpendicular and parallel to the shear plane, and then we have then the Lee and Schaeffer has derived that what is the the coefficient of friction along this chip tool contact length. Through that, the Morse circle diagram has been constructed, and the stresses at this planes have been carried over to the Morse circle at the periphery of the circle, that is the 2 dimensional, and then it was a simple derivation deriving the relationships of the angle, that is the phi, lambda and the alpha, that is shear plane angle, friction angle and the rake angle. Okay. So, we have seen that the relationship that has been derived by Lee and Schaeffer, that is very close to the derivation which has been made by the Merchants and Ernst. Okay. Although different principles have been adopted in deriving these equations and for looking into the mechanics of metal cutting in these 2 models. Next, we are going to discuss with you friction in metal cutting. Okay. Now, if you see in this slide, let us talk about first the nature of the sliding friction. What is sliding friction? That means when 2 surfaces slide on each other with respect to each other, what happens? Okay. So, here what we mean is that when they are sliding, the normal force acting at the interface is not very high, or let us say not as high as in case of the metal cutting. Okay. So, since the solid surfaces have asperities, asperities are the undulations like that, here it is shown, all right. The real area of contact differs from the apparent area of contact. So, the real area of contact will be on the asperities, on these when the 2 surfaces are meeting, this surface has asperities as well as that surface have the asperities. Mind it, these 2 are different surfaces. Let us say this is one part and this is another part. Okay. Apparent area is the geometrical area, which is let us say AA, okay, actual area. Now, in case when the load increases, the asperity deformation becomes initially elastic and then fully plastic, and the real area of contact is then a direct function of the applied load, independent of the apparent or the geometrical area of the surfaces. Next, here what is told in the second bullet is that when the 2 surfaces are resting on the asperities and the force which is being applied to the contact area, contact surface here. So, then these asperities initially they will be deformed, and they will be deformed elastically, and then gradually as the force increases further, this deformation becomes plastic, and then the real area of contact then, that is on the asperities which we have seen here, a direct function of the applied load is let us say n, normal load. Okay. That will be independent on the apparent area of or geometrical area of contact. See, here what happens, what we are saying is that when the force is very high, okay, then the real area of contact may be almost equal to the apparent area of contact. Okay. So, this is the equation that we get. Here you can see that this is independent of the geometrical area. So, on the geometrical area it does not depend, it is only on the real area of contact. So, n is the normal force here we are saying, and sigma y is the yield stress of the softer material. Out of this, whatever is the softer material, this is the yield stress of the softer material. Now, during sliding, this is the case. Now, when they are sliding with respect to each other, shearing of the welded asperities occurs. Okay. These asperities, since they are welded, because the force is becoming more, these asperities will be sheared, and the mechanism described by the adhesion theory of friction, okay, when it is like that. So, the adhesion theory of friction says that F, that is the friction force, okay, this is equal to the tau and the AR. Okay. Now, therefore, the mu, as we know, this is the coefficient of friction, this is F by n, friction force divided by normal force, and friction force is shear force into the AR, because friction is always because of the normal force, and that is along the surface on which the normal force is acting. So, therefore, it is the shear stress, and the AR is the real area of contact. Okay. Real area of contact, initially we said that these are on the asperities. So, therefore, the area on which it is actually resting, this is the real area of contact, and geometrical area or apparent area is the entire area irrespective of these asperities. Now, if we say that f is equal to delta and the AR, then n from here will be AR into the sigma y. So, therefore, AR is getting cancelled and this is tau divided by sigma y. This is the shear stress and this is the normal stress, or this is the yield stress of the softer material. Now, this equation shows that mu, coefficient of friction, is independent of the apparent area of contact. Okay. And since this remains sufficiently constant, because these are the material properties. Okay. You take any material and for that particular material the shear stress and the yield stress values will be constant, they are not changing. So, therefore, mu remains sufficiently constant. Okay. Because here of course, it is only the ratio of the tau and the sigma y. So, this is constant. So, therefore, mu remains constant. Mu remains constant means the f is proportional to n. Okay. Now, in metal cutting what happens, the coefficient of friction can vary considerably. Here what happens, we are saying that mu remains constant. This is for the sliding friction, normal friction where the force is not very high, okay, not excessively high, let us say. In metal cutting, the coefficient of friction, however, does not remain constant as in case of the sliding friction. The variance of mu, that coefficient of friction, results from the very high normal pressure that exists at the chip tool interface. So, if we see the cutting process, all right, let me draw it in this way, that again this is the chip being formed, this is the workpiece, okay, and this is the tool, all right. So, now as this process goes on, so at this point normal pressure is very high at the tool tip. Okay. Now, this very high normal pressure that exists causes the real area of contact to become the apparent, equal to the apparent area of contact over a portion of the chip tool interface, meaning that if the chip tool interface length is this, okay, the normal pressure is maximum here, but it actually decreases as you go up as along the contact length of the tool and the chip. Okay. So, therefore, we are saying that up till a certain distance, this apparent area of contact and the real area of contact become almost same, but beyond certain value of the length, this does not happen. Okay. This is what has been said here. Now, this is again, if you see this, the real area of contact is almost equal to the apparent area of contact, and the friction force is A A and the tau F. Okay. So, here what happens, F is now independent of the normal force, okay, and the ordinary law of friction then no longer apply. Ordinary law of friction is this, all right, that mu is equal to F by n, which is tau by delta y, and this does not remain anymore applicable, because in this case the force is very high, normal force is very high, and the real area of contact is almost equal to the apparent area of contact. Under these conditions, the shearing action is no longer confined to surface asperities. Okay. Now, what we said is that suppose in this case, as it slides, we said that the shearing happens of the asperities, okay, welded asperities. But when it happens that this is almost the same, then the shearing, then there is these asperities are welded all together. So, shearing happens, then of course, within the let us say this material is softer material. So, within the softer material, that is what it is said, that these conditions, at these conditions the shearing action is within the body of the softer metal. Now, model of orthogonal cutting with a continuous chip and no built up edge formation is offered by Professor Zorev. He is a Russian scientist, and he is telling that he is trying to define what will be the average coefficient of friction between the chip and the and the tool along the chip tool contact length. See, this is important because we said that it is no more the sliding friction, and here since the normal pressure is very high at this point. So, at the vicinity of this point to some length, at some length, the very high normal pressure remains, and therefore, the apparent area of contact is almost equal to the the geometrical area. So, f does not remain, f by n does not remain constant, okay. And that is what we said, that f is now independent of n, okay. But in this case what happens, that mu is equal to constant and f is dependent, proportional to n. But here f is now independent of n, and therefore, the ordinary law of friction no longer valids. Okay. What Dr. Zorev's model says is that the normal stress distribution on the tool face. So, first of all, let us see this diagram. This is the tool, okay, and this is the workpiece, all right. Here is the chip flowing along the rake face of the tool, and let us say at this point the chip loses contact with the tool, okay. So, from here to here, here it is designated as LF, this is the chip tool contact length, okay. That is the length at which the chip contacts with the rake face of the tool. Now, here the two curves are drawn, one is the normal stress, and this curve is for the shear stress, all right. Now, let us say that this is the point, okay, up to which the normal pressure remains very high. Let us assume that this is the point, all right. Now, beyond this point, that means above this point, the normal pressure does not remain very high, as let us say in this region, all right. And here what happens, the sliding friction rules still remain valid, because the in this length, along this length, still the high normal pressure is not very high. So, this zone where the normal pressure remains very high, it is called the sticking zone, all right, and where the normal pressure is not so high, this is called the sliding zone. So, as we have already discussed, in the sliding zone the mu remains constant, f by n is constant, like in the case of the sliding friction. But in the sticking zone, this is no more valid, because it is very high normal pressure, and f by n is not constant, and therefore, f is not proportional to n, mu is not constant, let us say. Okay. So, these are the two zones, one is the sticking zone, another is the sliding zone, okay. This is being the tool. Now, this once again, this is the distribution of the shear stress, and this is the distribution of the normal stress, all right. This of course, up to the point where the chip loses contact with the tool, with the rake face of the tool, all right. So, as you can see from this curve, that normal stress is maximum at this point, all right, and as it goes along this length, chip tool contact length, the normal pressure goes down, okay, along this length. And what happens to the shear stress is that here the shear stress remains non-linear, okay. We will show why it is that, and how you can get the equation. But here in this zone, that is the sticking zone, the shear stress remains maximum, okay, and the shear stress is constant everywhere, and this is maximum. Let us say this is equal to tau st. Tau st is the shear stress in the sticking zone, all right. Now, this length is the LF, that is the chip tool contact length, and this length is the LST, that is from the tool tip up to the end of the sticking zone, all right. This point, let us say from this point, if you go towards the tool tip, the x value actually increases. Let us say x value is 0 here, and as we go along this chip tool contact length, if we come to this point, the x value will be LF. If you are here, it will be LF minus LST, and so on, okay. So, therefore, the normal stress distribution on the tool face, this equation Okay. Dr. Zorep is given as sigma f is equal to q into x to the power y. Okay. Q and y, these are constant, and x is the value, is the distance along the chip tool face here, okay, from the point where the chip loses contact with the tool. So, as I said that x is 0 here, and as you are coming towards this tool tip, the x value is increases. So, x value is maximum where this LF, x is equal to LF. Okay. So, sigma f maximum occurs when x is equal to LF. All right. Now, the sigma f maximum therefore can be found out from the q, and the x is LF, then all right, LF to the power y according to this equation. In the value of in the place of x, we are putting the value of LF. So, this is the maximum then, because we said that here it is the maximum normal stress that occurs. Okay. Now, q from here we can find out is equal to sigma f maximum divided by Ly, LF to the power y, or sigma f maximum LF to the power minus y. So, therefore, sigma f, okay, from here if you put the value of q here, this will be sigma f maximum and the x divided by LF to the power y, because it is x to the power y and this is LF to the power y minus y. So, LF will be below. In the sliding region, let us say sliding region is here, okay, that is x is equal to 0 up to x is equal to LF minus LST. All right. At this region, mu is constant, and the distribution of shear stress in this region is given by, this is the distribution, okay, that this stress, that is the shear stress. So, the equation of this curve will be sigma f into mu, okay, that is normal stress into the mu will be the shear stress, and sigma f we already found out is sigma f maximum x by LF to the power y. So, this is the mu sigma f maximum in x by LF to the power y. So, it is just multiplied by mu with the value of the sigma f, which we have put it from the here in terms of the sigma f maximum. Okay. Now, in the another region, let us say I have repeated this drawing, so that it is understood here. Now, x is equal to LF minus LST up to the x is equal to LF, that is in this region what happens, that as I said the tau s or the shear stress becomes maximum, okay, which is tau st, all right. But the sigma f, all right, this is sigma f max x by LF that we got here. From here we can get actually the normal force, okay, if we integrate the area below this, and this will be and multiply by the width of cut, this will be the width of cut, and we are integrating sigma f max x by LF to the power y. Okay. So, once again in this area we have, or in this region we have the tau maximum, which is constant, which is tau st, which everywhere it is the same, and if we integrate the sigma f is equal to this that we derived, that we will get the normal force if we multiply by the width of cut, all right. So, this will also have the stress and the area. So, if we integrate this, it will be sigma f max AW, this will be the LF, and below will be 1 plus y, okay, because it is to the power y. Now, this is the normal force that we are getting by integrating the area on the sigma f, that is this, all right. Now, the friction force, to get the friction force similarly, we can actually have the integration of both of these, right, this and this value. So, this value you can see that, well, this value is easy because it is constant, tau st into the LST, LST is the length here, but for this we have to integrate, that is we have to take the area under this curve, and that will be from 0 x equal to 0 here up to LF minus LST here, and what we have to integrate is the tau. So, this is normal stress into the mu, Okay. What we have here, this we have to multiply by the mu. So, this will be the then stress, shear stress. So, then we are coupling them together, we are summing them up and we are getting the friction force, that is we are integrating the area under the entire curve of this tau, okay, from here to here and from here to here. From here we can find out that if we integrate, this is remaining the same constant, and then LF minus with respect to LF minus LST, 0 to LF minus LST, if we put the value, it will be this, okay, mu sigma F max, and then we will have the AW here, LF minus LST we are putting it to the power 1 plus y, because it is y here, divided by LF here to the power y, and again this 1 plus y will be here. So, this is a simple integration of this, all right. Now, we have the F and we have the N, friction force and the normal force. Then we can find out the mu, which is the coefficient of friction between the chip and the tool, and that coefficient of friction will be along the chip tool contact length. Okay. Now, we have to see if we get this F, and if we try to divide F by N, this will be very difficult to operate, in the sense that this has to be simplified. So, this can be simplified in the following way, that at that point x equal to LF minus LST. Okay. If you see that there are two stresses, okay, shear stresses, we have the shear stress here, and at the same time we have the shear stresses here, tau st, right. So, that is what we are saying, that at that point x equal to LF minus LST, the normal stress is given by tau st divided by mu here. Tau st is the maximum, divided by mu will be the normal stress. Now, we have the equation, we have derived this sigma f equal to sigma f max x by LF. If we now take this equation, all right. So, then the sigma f max LF minus LST will put it here in the form in the place of x, all right, divided by LF. So, this will be the normal stress, and that we multiply by the mu will be the shear stress. So, we have the shear stress as this, all right, and we have the shear stress as this, tau st we have, and we have this, all right. So, therefore, the tau st can be equal to mu and this factor sigma f maximum LF minus LST divided by LF to the power y. Okay. So, I will remind you that f we got it like this, all right, by integrating. Now, substituting this equation 3, what we got it here in the 2, that is f, then we are simplifying this factor, that this will be equal to tau st AW LST, this is remaining the same, but this factor is it is simplified. So, this will be tau st AW LF minus LST divided by 1 plus y. Okay. We are simply putting this value here, and we are getting here the tau st, this is important, all right. So, here the mu is gone, as you can see this. We try to avoid the mu and the sigma f maximum, which has been done here. Now, we can actually divide f, we can take the ratio of the f and n to get the tan of the friction angle, and the mean coefficient of friction on the tool face can now be expressed as this, all right. Why we are calling as the mean friction of coefficient? Because we have taken the sliding friction and the sticking friction, sticking zone, all right. So, therefore, whatever will be the mu now, it is not this or this, but it will be a mean value. Okay. So, this f we are taking this value, and that we are dividing by the n that we have got it here, this is the value n we got, and that is simplified, and then we get it this value, okay, tau st divided by sigma f max 1 plus y into LST by LF. So, this has been seen that this is the value of the tan of lambda, which is the ratio of f by n, which is actually the mu, and that mu we are saying is the mean coefficient of friction between the tool and the chip along the chip tool contact length, all right. Now, the mean normal stress on the tool face is given by, now we are saying about the normal stress. Okay. This is N, which is the normal force which is acting on that face, divided by the area. Okay. And the area is the width and the length. So, this is the AW is the width and the LF is the here LF is the chip tool contact length. So, in this we are saying that this will be the mean normal stress on the tool face. All right. So, this can be taken as sigma F max divided by 1 plus y, okay, that we have derived here. Now, therefore, the sigma F max from here we can find out as 1 plus y into sigma F average. All right. Now, you must understood that n value we have here, I have written down here. Put the n value here and that these things will be cancelled, AW and LF, and it will be sigma F max divided by 1 plus y. So, now if we substitute sigma F max, all right, then we will be getting it that lambda, this value in here, is equal to arc tan, tan inverse arc tan of this value. Okay. This is tau st and this all together. Now, in the experimentally it has been seen that tau st and this value, okay, that is the entire value of this, okay, this value, this remains sufficiently constant in the practice. All right. So, therefore, what happens that this is for a given material, of course, over a wide range of unlubricated cutting condition particularly, okay, because you understand that unlubricated is a condition, because when you are having the lubricated cutting condition, then of course, the mu comes into picture, all right, and it actually changes the condition. So, it may not remain so much of constant as we say for the unlubricated condition. So, therefore, what happens is that lambda is becoming arc tan of the constant, which is, let us say, some constant which is k. Okay. This k is the constant divided by sigma F average. Now, this is the equation, that is the conclusion of Dr. Zorev's model, all right, and this equation actually shows that the mean angle of friction is mainly dependent on the mean normal stress on the tool face. Sigma F average is nothing but the mean normal stress on the tool face. This explains the fact that as the normal working normal rake increases, working normal rake is alpha n, as it increases, the component of the resultant tool force normal to the tool face will decrease. Okay. So, as it is increasing, that is the alpha n, okay, this is the normal rake angle. So, let me give you this reference that the F, okay, cutting force and the alpha, we said that this is like this, all right, the it is a decreasing order. So, as the alpha decreases, the F increases. So, that is what we are saying, that the working, as the working normal rake increases, let us say this is n, because I said to you that this can be side rake, this can be orthogonal rake, or this can be normal rake. So, as the normal rake increases, the component of the resultant tool force normal to the tool face will decrease, okay, Fn, and therefore, the mean normal stress will decrease, this one, and the friction angle will increase. So, here what happens is that if it is increasing, so Fn will decrease. Okay. So, therefore, the sigma F average will decrease, and therefore, the lambda will increase, because it is inversely proportional. Okay. Friction angle will increase. So, ultimately what is happening, that as the alpha n is increasing, the lambda will actually decrease. So, this you can explain it only by this equation, otherwise it is very difficult to explain this fact that normal rake increases, then the the friction angle will friction angle will increase. Okay. Friction angle will increase, otherwise it is difficult to explain. So, this is the contribution of Dr. Zorev's model, that through a model and through the curves of distribution of the shear stress and the normal stress, he has shown what is the mean coefficient of friction in the chip tool contact length. Okay. So, because in the chip tool contact length the mu does not remain constant, and he has distributed that in the in two sections. One is the sticking zone, one is the sliding zone, and in these two zones, in one of the zones, as we have shown, let us say I'll just summarize that, as in we have shown that in the sliding zone the mu remains constant, and in the sticking zone the mu does not remain constant. So, within that he has shown that mu has to be some average value. Okay. And finally, he has shown that this is the relationship between the sigma f average and the friction angle, and as you know that friction angle, it has the with the relationship with the mu, because f by n is mu, and this is the friction angle, this is a tan inverse of f by n. All right. So, this is the gist of this Zorev's model, through which he is finding out the mean coefficient of friction between the chip and the tool during the metal cutting. Okay. Now, let us see the next what we will be discussing here are the practical machining operations. So, here schematically or pictorial views of some of the processes you can see, which you will also see in the lab. This is the, of course, the turning, where you can see that this is the tool and here is the workpiece. This is the milling process. So, here particularly the vertical milling is in the process. All right. This is the drilling. So, this is the drilling machine, and the hole is being drilled here, as you can see that this is the workpiece. This is the sawing, where we have the saw and the material is being parted, okay, cut. Now, this is broaching, which is an operation which is not very popularly used, because this is actually expensive operation. Okay. The broach, particularly the broach which is the tool for the broaching operation, this broach is very expensive, but with the broaching you can have the very fine surface, that is actually the property of the broaching. And the broaching can also have the, you can use the broaching process for making the internal slots, which is otherwise very difficult to get it. All right. And here the process is showing, here you can see that there the keyholes are being made, okay. Or in this case, this is of course the slots which are along the axis of the workpiece. These slots are being made for the shaft to go in, as you understand. And this is the shaping or planing, and we will explain later on what is the principle of shaping, what is the principle of planing, in which basically the flat surfaces are obtained, but also the inclined surfaces and the grooves, they can also be made here with the shaping or planing. Okay. Now, here what is shown here is the turning. Let us talk about turning first. All right. This is the pictorial view or the three-dimensional view. This is the workpiece, and the tool is here. Tool is mounted on the tool post, which is not shown here, and it is turning. So, the workpiece is rotating. Let us say this is the n, okay, RPM, and the material is removed as the tool is being fed along the axis of the workpiece. This is the axis of the workpiece. So, in one of the sessions, previous sessions, I have explained that this is the force which is the feed force, which is along the feed direction, that is why it is called the feed force. This is the radial force, this is radially directed, and they are summing on the horizontal surface. Okay. This is the Ft, which is the summing of the Fr and the Ff. So, once again I will remind you that it is somewhere made here, no. So, F t is the thrust force, this is root over F f square plus F r square. Okay. So, this is the thrust force, and the cutting force will be here in the vertical direction, and from this point to the front point below is the resultant force. So, the resultant force will be equal to F c square root over plus F t square. Okay. This is once again I am repeating. Now, these are the forces, and if we see the schematic, in this schematic it is shown here that this is the initial diameter of the workpiece, and this is the diameter which is being obtained. This from the tool has moved from this point to this point. Okay. Tool has moved from this point to this point with one revolution of the workpiece. So, therefore, this is the value from this point to this point, this is the value which is the value of feed. Okay. Whereas, the direction of the feed is this, or the direction of the feed is this is the feed direction. Now, from here to here, this is the width of cut. Okay. And if you take the cross section here like this, so what you will get is actually this view or the sectional view. Let us say the section we will take from here through this tool like this. Okay. So, this is the cross sectional view, let us say x x. So, this is actually the x x sectional view if we take the section through this, all right. This is the tool, not fully mentioned, it is hatched because it is sectioned, and this is the workpiece, this is the workpiece not fully shown here, all right. This is the chip being formed, the chip will be formed that you will see perpendicular to this face, you cannot see it here, but if you take this section then the chip will be visible, and therefore, if you take the tangent to this chip and then with respect to this rake face of the tool, this will be the rake angle alpha, and with respect to the flank angle is here, with respect to the flank face which is here, the workpiece already machined workpiece, this is already machined workpiece will make an angle which is called the flank angle. So, these are the these are the angles that I have shown it to you earlier also. Now, the geometrical parameters from the triangles from here, okay, let us say W, which is the width of cut, is equal to d by cos of gamma s. This in fact I already told you earlier. So, this you can find out from the triangle, this triangle, all right. From this triangle you can find out that W is here, this is equal to d by cos gamma s, and gamma s is here. This is the angle which is gamma s, side cutting edge angle, all right. This is in the ASA, that is coordinate system. And similarly, T1, which is the uncut thickness, this is equal to F, that is feet, and the cos of the side cutting edge angle. So, that you can find out from let us say this triangle, this small triangle. Okay. From this triangle you can find out that the T1, which is this is equal to F is here and the cos of gamma s. So, this is an important relationship of the physical parameters of the cutting process. So, as you can see that the F into D, okay, feed into the depth of cut, this will be actually width and the T1. This relationship comes from here, all right. Now, as far as the forces are concerned, Fr, this is the radial force, this is Ft and the sine of gamma s again is the side cutting edge angle, and the Ff is the Ft and the cos of gamma s, all right. So, this is the relationship of the forces with respect to thrust force, this is the radial force Fr, Ff is the feed force, and Ft is that on the horizontal plane. Now, the power, which is, as I said, is the product of Fc and the Vc. This here, as you can see, that this actually is the product of Fc and the Vc plus Ff into Vf. See, we have to consider the feed velocity as well as the feed velocity as well as the cutting velocity as well as the feed velocity. Okay. So, therefore, with respect to the feed velocity and multiplied by the ff is the feed force, this component has to be considered for making the for calculating the power. However, we say that Vf which is much less than the Vc, okay. Vc is much more. So, therefore, we actually ignore it, very often we ignore it, and the result that you are getting, that the power is a product of Fc and the Vc, this is not an erroneous, not so much of erroneous value. Okay. So, this is approximately we can say that if Vf is considered to be very less than Vc, we are ignoring that, and power is equal to Vc into Fc. Okay. Power can also be expressed through Uc and the MRR. Uc is the specific energy, okay, and MRR is the material removal rate. Specific energy actually is the energy required to remove a unit volume of material, as it is given here. Energy required to remove a unit volume of material, and this is given in joules per millimeter cube. Okay, the unit is joules per millimeter cube. So, Uc and this is the MRR. MRR is actually the area and the velocity, the product of area and the velocity. So, since it is turning, so the area will be the feed, okay, what you are getting here, into the d, which is the depth of cut. All right. This feed into the depth of cut will be the area of cut, you understand that, and velocity, this is the cutting velocity, this is pi d n by 60, and 60 is because this is RPM, revolution per minute. So, from minute to second we are taking. So, this will be millimeter cube, d is in millimeter. So, this is millimeter cube per second, okay, because n is RPM, this is revolution per minute, n which is given as the RPM, revolution per minute. Okay. Therefore, the Uc and the MRR, which will be power, this can be given as the U0 T1 to the power minus 0.4, which is Uc, okay, specific energy, that is U0 is a specific energy constant actually. This is the specific energy to remove 1 millimeter of T1. If you put 1 millimeter of T1, in that case Uc is equal to U0. So, very often you will find in the books that this is called the specific energy constant, all right, U0, and this is called the specific energy to remove 1 millimeter of T1. Suppose we have a rod which is being machined, okay, let us say cylindrical workpiece. This is the cylindrical workpiece, and the cylindrical workpiece has the length of L, capital L, and this is being machined with the feed of F. F is the feed, okay, and N is the revolution per minute, N RPM, okay, and in N passes, okay. In that case, the number of revolution per pass, this will be given by the whole length divided by F. You understand that the number of revolution per pass, this will be inversely proportional to F, because F is the advancement of the tool in millimeter, or advancement of the tool, linear advancement of the tool with 1 revolution of the workpiece. So, it will depend on the inversely proportional to F. More will be the F, number of revolution per pass will be less. Okay. Now, the L also it will depend on L, because more the L, more will be the number of passes. This is also obvious, because it will take more time. All right. Now, the time per pass, say therefore, it will be dependent on the n, that is, if it is rotating at a higher speed, the time taken will be less, and vice versa. So, therefore, it is inversely proportional to n. So, therefore, it will be L by F into n. Total time therefore, will be this L by Fn into the number of passes, okay, n, let us say. Number of passes means, suppose we have to have the depth of cut as d, okay, let us say this much of the depth of cut we have to take, and this depth of cut could not be taken in one go, for example. Suppose if it is very big, or the very large number. So, in that case it can be machined in 2 or 3 passes, okay, depending on what is the value of the depth of cut. If the value of the depth of cut is large enough, in that case it is we need several passes. Now, several passes also required when we need to have the surface finish higher. So, initially you take the larger depth of cut in the first few passes, okay, because in the first few passes you do not bother about the surface finish. Okay. The more the material removal, less will be the surface finish, by the way. And well, that we will explain in the topic that we will discuss on the surface roughness, surface finish. Now, the final pass or final 2 passes, you take very little depth of cut, so that the finishing operation can be performed and the required surface finish can be performed. So, therefore, in the few passes the entire depth of cut will be removed, and that number of passes has to be included here to find out the total time. Okay. And this is important because you have to find out the total time required, so that you can see that you can estimate what will be the cost of this part. Okay. More time it takes, the cost will be more, and that we will be discussing in the economics of machining. That would be very interesting. Okay. Now, let us see what happens in case of shaping and planing. Okay. Now, in case of shaping and planing, you can see that the forces which are acting during the process is different. First, let me tell you few things about shaping and planing. Of course, we will tell you in more details in the laboratory. We will show you the shaping machine and we will show you the shaping machine in action, I mean how the shaping machine works. So, both the shaping and the planing operations are used to get the flat surfaces as well as the inclined surfaces, all right, or the groove, for example. All right. Now, the tool that is used in the case of both shaping and planing, this is very similar to the turning tool. Okay, you can see that. Now, the difference between the shaping and the planing machine is in the quick return mechanism. Now, what happens is in case of shaping, for example, when the tool moves forward, it actually cuts, removes the material. Okay. Then it goes back to the initial position, ready to take the second cut or the second pass. So, during that movement, that is the tool moves forward and goes back, during that time this is actually called the stroke. So, during one stroke, that is tool moving forward and going back, the workpiece is moved, is given a feed, certain feed. Okay. So, it moves and then the tool will be or rather workpiece will be positioned to for the next cut, and the tool is moving again in the forward motion. All right. So, this length will be then increased. So, more and more, and finally, if you want to have a flat surface, the entire surface will be removed. So, let us say this much surface has already been made. So, this is a flat surface, as you can see, and then as the feed is given, this will be an incremental feed, in the sense that it will be given in after one stroke, it will go to some extent, that is the value of the feed, and then the next feed is given and so on. Okay. Now, during the backward movement, the tool does not remove the material. Okay. So, therefore, the tool moves backward at a higher speed, all right, and there is a quick return mechanism for that. Quick return mechanism makes the tool move forward at a certain speed and moves back at a higher speed. Okay. So, this quick return mechanism is different in case of planing and the shaping. In case of shaping, what happens is the tool reciprocates, that it moves forward and goes back. In case of planing, it is opposite, that is the workpiece moves to and fro and the tool is given a feed, all right. Because in case of shaping, normally the smaller workpieces are machined, and in case of planing, the workpiece lengths or the size of the workpiece will be much bigger. So, therefore, what happens is that you cannot make the tool travel at that length where it is too big. So, tool is in that case stationary for planing, okay, and the workpiece reciprocates. So, the stroke then will be the workpiece movement forward and the workpiece movement backward. At that point, after one stroke the tool will be given a feed perpendicular to the direction of the stroke. Here for example, the shaping is shown. So, shaping tool reciprocates and the feed is given in the direction perpendicular to the movement of the tool. All right. Now, as I was telling that the forces which act here on the shaping and the planing both, these are different. Now, here it is the feed force. Feed force will be also along the direction of the feed. Okay. This is the normal force Fn, and the normal force is perpendicular to the already machined surface, this surface. So, their summing up of the Fn and Ft will be Fn and F will be the Ft, meaning that F square and Fn square root over will be the Ft. Okay, like in case of the turning, but in turning it was the radial and the feed force. All right, here it is the feed force and the normal force. Now, the cutting force will be directed perpendicular to that, perpendicular to the this thing, and along the VC, perpendicular to this tool edge and along the VC. VC is the cutting velocity, all right, and the cutting velocity in this case is the movement of the tool, because tool reciprocates, it moves at a higher, it moves forward, and at a higher velocity it moves back. All right. So, this is the cutting velocity, and the feed velocity is given to the workpiece. All right. So, Ff here is the Ft and the cos of gamma s, as in case of the turning, and similarly the Fn is the Ft and the sine of gamma s. Okay. Now, in this case the gamma s is this angle, gamma s is this angle, and this angle in case of shaping it is called the primary principal cutting edge angle. Okay. This is the difference between the gamma s in case of turning and in case of shaping. Here this is the gamma s. All right. Exactly for you to see this, suppose this is the tool. Okay. So, this is the one, I mean here. Okay. This is the primary principal cutting edge angle, because this is the principal cutting edge for the tool. So, this is the schematic diagram, this is the 3D picture, and here you can see the geometrical parameters. Geometrical parameters are that this is the feed, that means the movement of the workpiece here, that because the feed is given to the workpiece, all right, along the direction of perpendicular to the VC in one stroke, this is the feed, because as I said the tool moves forward and then it goes back, then only the feed is given. So, this is the F, this is called the feed. All right. Similarly, this is the depth of cut, and the other parameters which are here I will discuss in my next session of discussion. Thank you for your attention.